You're listening to MedX, the Medical Extrusion Podcast, presented by U.S. Extruders. Extrude with confidence, custom extrusion equipment designed for you and your application.
Hi, folks. Welcome back to the MedX Podcast. Today's guest is Ross Peterson, Chief Business Development Officer at ProPlate. ProPlate specializes in engineered custom coating solutions for metallic and polymer-based catheter components. Very interesting conversation with Ross. I hope that you enjoy. Hey, Ross, welcome to the MedX Podcast.
Thanks so much for having me, Steve.
Yeah, I'm really glad to have you on, and I'm really excited to talk about this technology to add radiopacity to components and medical devices. So let's get right into it. And before we get into those technologies, why don't you just kind of give us a high-level background of who ProPlate is and what you guys do?
Sure. ProPlate's been around since 1984, and the current ownership has owned it since 1997. We've been focused on the medical device industry for the past 25 years, and we've really honed in on it for the last 15 years with some of these technologies that we're going to talk about today. Mm-hmm. We are ISO 13485 certified, and we actually have two locations. Both of them are in Anoka, Minnesota. The first one that we started in was 12,000 square feet, and we still operate out of there today. And the second one is 38,500 square feet, which we're just moving into this year, midway through 2024. So we do have a lot of room to grow.
Oh, congratulations on the expansion.
Thank you.
Let's talk about radiopacity and more specifically the Vizi-Band technology that allows you to coat radiopaque coatings onto stent strut frames, laser cut hypotubes, and other metallic components. Can you give us an overview of that technology?
Certainly. So I'll give you a high-level overview of the process to start, and then we can talk about some of the features and benefits that it offers.
Sure.
So what we do is we'll take like you mentioned, a hypotube, stent, or similar component that might need a marker band or even a ring electrode on it. From there, we'll apply a liquid polymer to it, and that acts as the masking. And then we'll move into a laser ablation process that selectively removes the areas of the component that we want to expose for the plating process. So we'll have a bare metal surface in those areas. Then we can move to the plating process, which involves a series of activation and cleaning steps, followed by the actual plating step itself. Those activation and cleaning steps simply remove any residue that's left on the parts, and they'll actually activate the surface as well to create free radicals for bonding and promote adhesion. In the plating bath, you'll have metals that are in the form of an electrolyte solution that are ions suspended in this bath. It's an electrochemical process. And you apply an electrical current to the parts through either a rack or a barrel fixture. And in most cases, actually, it's with a custom fixture that we've built in-house, because most of these parts are so unique and their requirements are unique around them. After applying that current to the parts become the cathode. And in the bath, there's an anode as well, which pushes those metal ions onto the parts, building up microinches at a time. And it's actually a very effective and efficient way to layer metals onto another. With the Vizi-Band process for radiopacity, we're using either gold or platinum, and different thicknesses depending on the application.
Okay. I know that I did an unboxing recently of this compression wrap. It's an expanded PTFE compression wrap, and it's used as a manufacturing aid when encapsulating stents, so that if you have an inner and outer layer on the stent and it's put in an oven, this wrap compresses it and bonds the two layers together, but it also protects the scaffold from direct heat during that process. And I know it's important for nitinol in particular because nitinol's heat sensitive. So just wondering, when you're applying these coatings to a temperature sensitive material like nitinol, are there any special handling or processes that you have to go through for some temperature sensitive materials like nitinol?
Certainly. So nitinol and, well, I guess plating will create hydrogen. And we don't want hydrogen to be embedded into the plating or the part itself, especially with nitinol. That can cause embrittlement. So there's a series of steps that we can take in the plating process to help reduce the amount of hydrogen that's created. But you can't completely eliminate it, the plating side itself. So then afterwards, we can do a low temp bake to relieve the hydrogen as well. And everything is below about 200C or 400F. And so we're not negatively impacting the shape memory properties through thermal energy.
Okay. I noticed, I'm going to share a picture real quick. So here's an example of a laser cut stent, right? And this gold plating, is that the plating that you've added onto this stent for radiopacity?
Correct. That would be a
Okay.
gold plating on just the OD of those struts. And
Okay.
it looks like we might be avoiding the side struts as well.
Gotcha.
There's actually there's an intention behind that. So with these, especially nitinol, but these stent-like structures, whether it be a heart frame or even a neuro stent, when you make a circumferential band around that structure on the strut, you absorb a lot of those shape memory properties or mechanical properties. And so with our coating process, it allows us to just coat or plate the OD only, or even in some cases the OD and the side struts, but avoid the ID of any plating. And this can be an advantage for the shape memory properties and flexibility, like I mentioned. But there's several other advantages to using a plated marker band with our Vizi-Band process versus a traditional marker band. We can also reduce the profile because we're using an additive process to create the marker band. We're not really limited in terms of thickness, with the exception of what shows up bright under fluoroscopy. Those typically range between 0.2 to about 0.8 of a thou that our customers find adequate radiopacity, but we don't really have a limitation on upper end of the thickness. We can plate several thousand of gold and up to 1 thou of platinum.
Okay. Yeah, I guess it just matters what the application is, what it's being absorbed against, and how thick you go, right?
Yeah, it depends on the application and where in the body it might be used, what anatomy might be over, and absorbing some of those so that you can have some differentiation between that part of the component and the rest of the component. And then there's some other advantages too in terms of shape. So with the coating process, we're not limited to band shapes. We can make helical patterns or spiral patterns, which then offer the ability to see device orientation as well as location. So what you normally have to take semi-circumferential bands, cut them up, and glue them on or weld them on. And it's a really tedious process that isn't very scalable, which kind of leads me to one of the other major advantages of this process is it's a highly scalable process. As I walked you through the process steps before, you'll notice at the end step, one of the most important steps, which takes the most amount of time in the plated bath, that's a batch process. So to make one band on a given component, it takes the same amount of time that it would take to make 100 on that same component.
Yeah.
It's just a little bit more material, but that's not the biggest cost driver in this.
Yeah, I was going to say, adding swaging, crimping, these processes when we're talking about miniature products can be very, very difficult and complex. And I don't know what the yields look like, but I would think that to be able to selectively coat would certainly be more efficient manufacturing process.
It certainly can be. And as I mentioned, if we see a device that needs about 3 discrete marks on it or more, that's where we can be very cost competitive and sometimes be a better cost alternative to traditional marker bands, like you mentioned, swaging, crimping, welding, and sometimes even gluing, which leads you to the next advantage of this technology is the risk of dislodgement is essentially eliminated. This process creates a bond at an atomic level. So it would take enough mechanical force to destroy that component before you remove any of the gold or the platinum from it.
Wow. Great selling points, Ross. All right, that was really cool. Let's move on to the MediPoly and the ability to add metallic coatings to plastic parts. I was at MD&M Midwest, and I know you were there too. And I had a chat with Teddy Mudge from Hoop Medical, and he was sharing some insights into the work that Hoop does to add metallic or electrodes, sensors, devices to the body of balloons. And so I wanted to talk to you about the technology that you offer to provide some selective coating over polymers. And what I'm really interested in learning through your description of this technology is how you're able to do it without degrading the polymer.
So I guess I can start with a background story on where this started for us. We also, as you mentioned, at trade shows, we've been going to a lot of trade shows over the decades of us being in the industry, and we listened to our customers and found that there really aren't good solutions for adding these electrical features to especially balloon catheters. And so that's where we started to put our focus on and try to think of ways that we could come up with a solution for that problem. And we explored electroplating methods to electrolessly plate, I guess, so not really electroplating, but plating methods to metallize catheters. But we found that, to your point, a lot of those chemistries will degrade catheters or the polymers, and it would require a lot of different chemistries, so a lot of floor print to have the right chemistry for every single polymer out there. Then we decided to explore the world of vacuum deposition, where we found a particular blend of vacuum deposition where we took some of our own learnings, could create thin film deposits on these 3D flexible polymer components for electrodes that would enable mapping, ablation, stimulation, and sensing. And there aren't really any good alternatives out there today. This is a very new technology that the alternatives are adhesive back foils, conductive inks, things that don't stretch well or adhere well to the component, especially in the nature that it's used for expanding balloons, expandable balloons. And so we think that we have something really unique. And with that, we did get a full patent for this technology that we call MediPoly.
Okay. A lot of these balloons are highly compliant, very soft. And how do you kind of match the compliance level, soft, stiff, of the metallic coating to the balloon material?
Yeah, that's definitely a challenge. And, to circle back to your original question with thermal degradation, that's also something that we have to manage with this process as well.
Yeah.
We did melt many balloons in the early stages of this technology, and when we're developing a new process, that sometimes can occur. But once we have that down, the process itself and the metal itself, we're applying it at typically pretty thin thicknesses.
Yeah.
But then also the process itself, it creates grain structures that are more stretchable. And then we're even applying the balloon in an expanded state so that, when that goes back to that state, when it's being used, you're not going to have delamination or cracking of those metal layers. But each application is different. So the thicknesses can definitely range depending on if it's being used for ablation or stimulation or sensing, like I mentioned, for those potential uses.
Okay. Some of those characteristics of the bond strength, durability, maybe even corrosion, are there certain test methods that you use to test these characteristics?
Yes. So we've had to create some new test methods, but there are some ASTM standards out there that we use too.
Okay.
There's an ASTM tape peel adhesion test, which is similar to an electroplated metal and metal bond, where you take pressure sensitive tape and you press it onto the deposited area, you pull it off at a 90-degree angle, and you look for any signs of delamination. So that's a good test for tensile strength of the adhesion. But then there's cycle testing that we'll collaborate on with our customers that can cycle the balloon, inflate it, and expand it, stretch it, manipulate it, and then also test for adhesion in the same way afterwards. And then corrosion testing, we are using inert materials for this process, so we're not really concerned about that, but it always comes up, whether it be galvanic corrosion or just corrosion in general, where customers have those concerns. And so we can do accelerated saline soaks, which we have done, to prove that the metals will not corrode even in a saline environment over time at an elevated temperature.
Okay. Excellent. Thanks for going through both of those technologies. Very interesting. And thanks for coming on the podcast. And thanks for sending me this sample box, which I'll share with the folks this Saturday, hopefully open it up and share the contents. But kudos to your marketing team, or you, that put this together. Really nice presentation. Sales folks are always looking for samples, and this is I really like how you put this together with a little spec in here and the samples, and I'll share that. But kudos, good job on that.
Thank you so much, and I really appreciate you taking the time to have me on the podcast, and look forward to coming back sometime in the future.
Yeah, we'll get you back. We'll talk about magnets next.
Thank you for listening to MEDEX, the Medical Extrusion Podcast, presented by US Extruders. Please subscribe to make sure you're getting the latest episodes. For video episodes, go to us-extruders.com/podcasts. All links are available in the show notes.